Welcome to AP Calculus Definite Integrals Part 2. Volumes of solids with known cross sections. In this case, we will look at the base of a solid that is in the plane of a certain shape, and then cross sections of that solid are also a certain shape, and we will find areas of those cross sections and then use a limiting function to find the volume of adding all those areas together. Alright, let's see what's going on visually. Alright, the first one that I'd like you to see is a circular base, and the cross sections are circles. This is just like the one I showed you in class, and it will also be our first example. Alright, let's use cross sections that are squares. The base, as you can see, is still a circle, but the cross sections are all squares. I like how it goes down to a little point right there. And if you look at it from the top, it's hard to see, but it's still a circle. Cross sections are all squares. Pretty crazy. Alright, I think that'll do. Now let's go ahead and look at the examples. No, the formulas first. And here come the formulas. For cross sections of area A of x taken perpendicular to the x-axis, the volume equals the integral from left to right of the area function of x dx. That ax is for area, cross sections of area. For cross sections of area A of y taken perpendicular to the y-axis, the volume equals from bottom to top the area function of y dy. Alright, let's go ahead, move on. Okay. Solid has a base that is a circle with the equation x squared plus y squared equals 1. Cross sections perpendicular to the x-axis are semicircles. So each of these cross sections, as we slice it, would be semicircles going across like that. And the diameter of the semicircle is going in the plane of the base. Find the volume of the solid. So, first thing we're going to do is we need to solve that equation for y so that we can have a radius, basically. Alright, so cross sections are semicircle. Okay, what's the area of a semicircle? That would be pi r squared over 2. This r, that will be whatever we solve y for. So let's go ahead and subtract x squared from both sides. So y squared equals 1 minus x squared. Take the square root of both sides. So y equals square root of 1 minus x squared. Alright, now from left to right, right here to here, if the equation is x squared plus y squared equals 1, the radius is 1, so that's negative 1, and that's 1. So we are going to find the volume is going to equal the integral from negative 1 to 1 pi r squared over 2 dx. Wait a minute. This is our radius right here. So volume equals the integral from negative 1 to 1. Let's bring the constant out front. pi over 2. And then that would just be the square root of 1 minus x squared, quantity squared, because that's the radius, squared, dx. So volume equals pi over 2. Okay, I think we can take the integral of this. That would be x minus x cubed over 3, evaluated at 1 and negative 1. And when we do that, the volume equals 2 pi over 3 units cubed, whatever those units are. And that is the volume of a solid that has a base of a circle whose cross sections are semicircles. Moving right along. Example number 2. The base of a solid is a region enclosed by the graph of x equals y squared, the x-axis, and the line x equals 4. Cross sections perpendicular to the x-axis are squares. So what you've got are squares that are coming up. Alright, so once again, we need to solve that for y because we're perpendicular to the x-axis. So here we go. Take square root of both sides. Wow. Square root of x equals y. Okay. Here's 0. Here's 4. Those are, okay, what is the area of a square? Area of a square equals one side squared. This right here is one side. So this is going to be a very easy one. Volume equals the integral from 0 to 4. Square root of x, quantity squared, dx. So volume equals the integral from 0 to 4 x dx. So volume equals x squared over 2, evaluated at 4 and 0. The volume equals 8 units cubed. Not bad, eh? So that is the volume of a solid that has a base bounded by the x-axis, x equals 4, and the equation x equals y squared. And it's always good to draw a picture with these. Alright, here you go to the last example. This time we're going to have cross sections that are perpendicular to the y-axis. The base of a solid is a region enclosed by the graphs of y equals 0.5 x squared and y equals 8. Cross sections perpendicular to the x-axis are semicircles with diameters in the plane of the base. So what we have are a bunch of diameters going, wow, nice line there, diameters going on here, and up coming from those you've got semicircles that are coming. Alright, so let's see here. We need to go from bottom to top. There's 0. There's 8. We need to solve this for x, because it needs to be in, wait a minute, we're doing semicircles again. Okay, what's the area of a semicircle? Equals 1/2 pi r squared. The radius will be our function of y. So let's solve this equation for x right now. Go ahead, I dare you. Multiply both sides by 2. Take square root of both sides. So there is my function of y, which will serve as our radius in this case. So the volume equals the integral from 0 to 8, 1/2 pi times the root 2y quantity squared dy. Let's go ahead and pull that constant out front, pi over 2 times the integral from 0 to 8, square that, and you just have 2y dy. Well, this is going to be a really easy one to integrate. Volume equals pi over 2 y squared, evaluated at 8 and 0. Our volume is 32 pi over 32 pi units cubed. And yeah, your homework will be a little bit more difficult than this. The difficulty is not in the integration here. That's not it. It's setting up the correct formula. And if you're nice and ask me nicely, I might even show you in class all the formulas for the different cross sections. Yeah, because when we get to equilateral triangles or 45, 45, 90 triangles, those can get a little bit crazy, but not too bad. So make sure you are nice to me and ask me nicely in class, and I might show them to you. This does conclude AP Calculus Definite Integrals Part 2, volumes of solids with known cross sections.